everyone. Hello, Bajo. Sat Sri Akal and Namaste from my side. How are you all? So, this is your own physics educator Indrajit Singh welcoming you all onto the most sensible platform as usual. I heartily apologize for the yesterday's lecture. Right, it didn't went on. I really apologize, and I think since 1.5 years has been crossed and I've joined PW. Okay, it not went a single day and I would be absent since 1.5 years into the PW, whether it is Diwali, right, or even right, my birthday. Okay, nothing went like that. Indrajit sir is absent, right? From the back end also, every time I used to get my reviews, okay, that Indrajit sir is never, what we can say, late in his lectures, and we always used to move on into the advance. So this time it went on weird, right? It was quite weird for me even to manage also, because on the Sunday afternoon I suddenly got a news about my Nana ji, right? And okay, he's no more. Obviously his age was right, more than 85, but it's okay, it hurts. Okay, if someone who is near, and I spent a lots of time with him, and even I've roamed many parts of India, right, with him, like even more about the northern part. So it felt right, I'm feeling guilty right now, so that's why I'm really apologizing for that part. Okay, the first time since 1.5 years, was the first time it went on that Indrajit sir is not in lecture. Okay, 3 to 4 months back it happened that as of some sudden emergency I have to move on for 3 to 4 days. So for that purpose also, right, I gave my extra time and recorded all of those lectures previously and was given to the team, so that the study of the students won't get hampered. But this time it was a sudden call, okay, and immediately me and my mom dad, we moved on, right, to that specific area. And as of that purpose, the Sunday, right, late night I picked up the flight, early morning, right, I reached to the specific place, right, all of those rituals and everything I attended. Okay, it was wasn't necessary, but this lecture was also important. Okay, because it was what we can say, a spot that this time Indrajit sir left. That no, I can't agree with that. Okay, Indrajit sir is never absent to the lectures and is never going to be happen. Okay, because it's not part of my inner, what we can say, it's not a part of my nature, right? So it won't happen. Okay, and after completing, say, I think late night Sunday, we picked up the flight with my mom and dad, and immediately I went on. Right, we reached early into the morning and we performed rituals yesterday and everything, and again I took a flight late night yesterday. Okay, and early into the morning right now. Okay, I'm into the home, and especially since I think approximately 26 hours I haven't slept, right, and still after completing this lecture I will have a sleep for a while. Okay, so it felt really guilty to miss a lectures, right, because this is a course excellence batch that we declared for, that it should be onto the regular basis, and if on the single day if I'm missing something, right, and obviously it is going to be the disaster for the students, because the bridge between you and us is going to get break. Okay, so kindly apologize for that. So guys, I think it's time to move on. Today we are going to start with the new chapter, right, from now onwards, right, it will. इंद्रजीत सर कभी बीमार भी हुए हैं ना, तो भी खड़े रह के लेक्चर लिया है. इंद्रजीत सर का गला, लाइक आई व्हेनेवर यूज्ड टू हैव अ सोर थ्रोट, then also I have taken the lectures. Okay, because this is only the time, the quality time I'm spending of my entire life, of the entire day, right, recording the lectures and interacting with you all. This is only the quality time apart from my, right, personal life, right, from the professional life. This is only the quality time. It doesn't mean that whatever the discussion is going on with an else team is not a quality time. It is the more, right, I like about this is to conduct a lecture. That's why. Okay. So I think, okay, let's keep these things apart. It happens. Right. Okay. Now let's move on to you are the unit of power, Harry. Right. And this side resistance is futile. False. Resistance is volt per flow of the electric current. So today we are going to discuss in detail about the electric current. Okay, the first lecture would be quite small. Please don't get worried about it, because today we are only going to discuss about what is electric current, what is an average value of the electric current, what is an instantaneous value of the electric current, what is a current density, right? And after current density, right, the detailed analysis of the current density, the relation between the current density and the field through the resistivities and everything. Okay, and the drift velocity. Let's see if we can complete drift velocity or not, or else, right, tomorrow with the Ohm's law we are going to complete with that part. Right. So are you all ready? This is what, after 26 hours of being awakened, right, we are here. Okay, so now let's move on to it. Current and current density. So electric current. In this lecture, students are having a myth. Lots of confusions. What kind of the confusions? Because somewhere they might have read it. Somewhere they might have read, or somewhere they might have heard that moving charge produces electric and magnetic field. Stationary charges shows electric field area around it, while the moving charges shows the electric and magnetic fields. Right? Electric and magnetic fields. So in this case, what happens? Right? In this case, what happens? We are talking about the current. In this chapter, see, before moving on to this chapter, I want to clear out a thought. Okay, I want to clear out a very simple thought, that in this we are going to deal with the moving charges, because moving charges has a capacity to constitute the current. Moving charges has only a capacity to constitute the current. Now in this, what happens? A charge that is moving has the capability, right, okay, to produce an electric field and magnetic field both. But right now, whenever we are dealing with the current and current densities and everything, okay, from theory point of view, practically, if I am saying that charges are moving from one point to another point, right, then I can't regret that magnetic field is not present. But whenever we are studying up the theory, individually we are teaching up. So individually, when we are focusing on the specific flow of charges, that is electric current, the magnetic field effect is completely avoided. Magnetic field effect is completely avoided, mark my words. Right? Magnetic, again and again I am saying, the magnetic field effect is completely avoided. So in this right, whatever the concepts are going to come, in which we are going to deal with the moving charges. So at the whatsoever point of time, if we have a doubt, right, then why this magnetic field is not considered, then simply the answer is we have avoided it. After this, whenever we are going to deal with the galvanometers and everything, okay, how galvanometer works, then we are going to take the magnetic field into the consideration. Okay, when we will move on to the moving charges and magnetism. Okay, the syllabus is designed in such a way. Electrostatics and capacitance, right? Electrostatics is about the static charges. Capacitance and current and electricity, it is about the moving charges, but only electric effect is considered. Moving charges and magnetism, magnetism and matter, alternating current and EMI, electric and magnetic field, both effects are considered. And then comes the combination of electric field and magnetic field, electromagnetic waves. Okay, so likewise the syllabus is, the entire syllabus is designed, and then suddenly it starts with the ray optics. Okay, and then it starts with the wave optics, the complete optics part, and the modern physics. So this is how the entire syllabus is designed. Okay, this is how the entire syllabus is designed. So we have to think up into that way. Okay, So the main purpose of conveying, right, the message is you have to avoid the electric field by understanding the concepts of the current and resistances, right? So what is an electric current? Flow of charges per unit time. Simply, I want to define the value this current, right? Flow of charges per unit time. I, that is equal to Q by T. In another sense, I can say the current is about how much number of the electrons or number of the charges are crossing per unit part of a conductor per unit time. Okay, per unit part of the conductor will define something else. But if I am saying that this is an area, right? Right now, not I'll make it as much complex, right, as what I want to convey. Simply, from a point, let's say from a point A, right, how much number of the charges are crossing per unit time. In an entire conductor, we are defining a single point. You can just point it out at any way, right? Or you can just mark this pointer in any part of the conductor, right? At any point on the conductor, how many charges are flowing per unit time. This is a gate of the PW Vidyapeeth. Okay, let's have the very simple example about it. This is a gate of the PW Vidyapeeth. If the gate is open, how many number of the students can enter from that point? How many number of the students can enter per unit second? Sir, fans of PW, lovers of the PW. Please, I heartily apologize for saying fans of PW. No, you are part of PW. Okay, so PW peoples, PW students, right? N number of the PW students can cross that specific point per unit second, and this N number depends on, right, the love, the affection the students holds, the emotions those students holds towards the PW. Right? I heartily, if sentiments of someone's are getting hurted, I heartily apologize for that again and again. Some students might be thinking, those who are watching of this lecture, that there is lots of apologies, right, you are having in front today. It happens. So without wasting my time, let's move on to, you can have the visualization of it. Through this specific point, how much number of the charges are crossing per unit time? Okay, how many number of charges are crossing per unit time? That simply defines the flow of the current. Second point, is current a scalar quantity? I will define the current as tensor quantity. Basically, when we are dealing into the physics, we are not having the two types of the physical quantity. We are having the three types: the vectors, the scalars one, the vectors, and the tensors. Scalars are having only magnitudes. Vectors has magnitude and the direction, while the tensors, right, are those physical quantities, right? See, if I'm talking about the vectors, so they are having magnitude, they are having direction, and they follow the triangular law of vector addition. They follow triangular law of vector addition. But if I'm talking about the tensor quantities, it has magnitude, it has direction clockwise and anti-clockwise, but it does not follow the vector law of addition. So this is the third, this would be the third category of a physical quantity classification, right? Okay, so current is nothing else but the tensor quantity. Tensor quantity itself states that it is having the magnitude. Yes, this much amount of the charges are flowing, right? It is measured into the ampere, right? Ampere is the unit. Okay, so I must say at this specific point 3 ampere current is flowing. Ampere is a unit, na? So 3 ampere current is flowing. Into the clockwise or anti-clockwise? Yes. Into the clockwise part of the circuit it is flowing. Yes. So but being clockwise, anti-clockwise into the specific part of the circuit, I can't say current is moving towards positive I direction, current is moving towards negative I direction, right? Positive J, negative J. I can't convey that. I can't demonstrate that part. Though this current is having the direction, right? We can say the current is flowing into the clockwise direction, it is flowing into the anti-clockwise direction, depending on how, right? Depending on how the batteries are connected. Depending on how the batteries are connected. We can say that it depends how battery is connected, but still something lags behind. So in that case, we are not able to identify the direction of the current. So as of that reason, we are saying the current is having only magnitude. It is having the direction clockwise or anti-clockwise, but right, it does not follows the triangular law of vector addition. Now the scientists were getting confused. We are having the physical quantity, right, that is having the magnitude and direction both, but it is not, it can't be, right, what we can say, vectorially added. Algebraically you can add up these currents. The entire Kirchhoff current law is based on algebraic summation of the current. Though current, right, is having the directions, then how it is possible that it can be algebraically added? This is the power of the tensor quantities. Okay, later this tensor quantities you are going to deal within the next part of this, right, somewhere into the after 12th, whenever you will move on to the syllabuses, right? So current, the flow of charges per unit time, it is a tensor quantity, ampere is a unit of the current. Now we are going to deal with the two values of the current. The one that is an instantaneous value, the second that is an average value of the current. This is a difference, okay? Okay, students should all aware of. There is a difference. What is an average? Okay, we have seen into the kinematics, the 11th standard 3rd chapter. Okay, we have seen that what is this average velocity and instantaneous velocity, average speed and instantaneous speed. Okay, the same thing comes up here. What is an average value of the current and what is an instantaneous value of the current? Let's take a cylinder. I'm talking about a point on the cylinder, right? Cylinder is connected to the positive terminal of the battery. Please mark my words. This is a battery. This is a symbolic notation of the battery. From now, see, entire chapter is based on DC supply. Right? In this chapter, we are not moving on to the comparison between the AC and DC or how it differs, how DC differs from AC. Okay? At the beginner's level in this chapter, we are only going to deal with whatever we are things that will come up, it will come up with the DC supply. There may be the combination of the batteries, right? There is a possibility that this supply may differ. Whether single cell is connected or single battery is connected, where n number of the cells are connected in series and so they are supplying, right, the power to the circuit, right? Or n number of the cells, they are connected in parallel and the resultant terminal voltages are getting applied to this specific circuit. We are not dealing with that part. What is a terminal? Some students might be thinking, the long things you are picking up, right? Lamba फेंक के मार रहे हो, terminal voltage and everything. Each and every part of this terminologies will be get cleared. Don't get worried. At this moment, just accept we are going to move on with the DC supply. Right? Now, if I'm talking about the point A part of the circuit and the number of the charges flowing per unit time. Okay. The important thing that we missed about the direction of the current. The direction of the positive charges is the direction of the current. You can see, right? In this visual, it has been shown. Direction of the positive charges. Current always flows from the positive terminal of the battery to the negative terminal. Right? Positive terminal of the battery to the negative terminal. Okay? So here, suppose here the positive charges are moving like this way. Positive charges are moving like this way, right? At specific point, it doesn't mean that they are crossing entire conductor. It takes lots of amount of a time for an electron, right, to move on, right, throughout the conductor. That is also we are going to see. Okay, suppose they are crossing this specific point A, as I told you all, right? Okay, at t is equal to 0, we switched on the battery. Kindly, okay, if you want to note it down, please note this down. At t is equal to 0, right? Okay, we switched on the battery. At t is equal to 0, we switched on the battery. Now in this case, what is actually going to happen? Suppose if I'm talking about t is equal to nth second, in between 0 and nth second, the number of the charges flown per unit time is current, average current. Okay. Simply, if I want to define technically, then I can simply say that average value of the current, flow of the charges per unit time. From an example, in between t is equal to 0 to t is equal to nth second. Let's say this nth second can be 1 second, can be 2 second, can be 3 second, can be 4 second. In between 0 and 1 second, how much number of the charges flown per unit second? In between 0 to 2 seconds, how much number of the charges flown per unit time? Right? In between 0 to 3 seconds, how many number of the charges flown per unit time? In between 0 to 4 seconds, how many number of the charges flown per unit time? Right? So this is all about charges. Right? This all is about, okay, the time interval. Exactly, the specific word is the average current is all about the time interval, right, in which the number of the charges flown per unit second. Average value of the current. Right? Now, what shows the instantaneous value of the current? What shows the instantaneous value of the current? Let's say, again, we are taking one conductor, right? And the conductor is given the supply, right? This is a positive terminal, this is a negative terminal. Again, I am defining the point A, right? Through supply, charges are moving, okay, at the specific point A, right? Suppose at t is equal to 0, the battery switch is on. Right? Suppose at t is equal to 0, the battery switch is on. Okay? Battery switch is on. So what happens here? Right? How much number of charges are flowing on third second? How much number of the charges cross this point A on third second? There is a difference between the average and instantaneous value of the current. Average value of the current states in this much time interval how many number of the charges flown through that point. Flow. Instantaneous value of the current states that at this time how many number of the charges are flowing. If I'm going to compare the instantaneous value and the average value of the current, then simply we want to take an example of day-to-day life. Okay, let us take an example that when on the Sunday afternoon we heard, right, he was kept at the ventilator, okay, in the early morning, and when we heard into the afternoon that okay, the monitor is not showing any kind of the readings, okay, the heartbeats values were to 0, and at that point of time, okay, we started our journey into the evening. I must say, suppose let's say we started our journey at 10 p.m. In between 10 to 12, how much distance we covered? How much distance we fly? at 12, what was my position? That is the difference. One side we are talking about the entire span of time. At one side we are talking about the moment. So instantaneous value of the current states that at a specific moment, the number of charges flowing per unit time at a specific moment, number of the charges flowing per unit time. It means that when battery is switched on at t is equal to 0, right, at t is equal to third second, right, this much amount of the charges are flowing per unit time. The value of the current, let's say it is 2 ampere, right, at t is equal to fourth second, right, let's say the value of the current is 8 ampere. Now the students might be having a doubt, sir, how the supply is given, the value of the current is changing. Better, this is a battery connected with the voltage regulators. Okay, whenever the DC supply is connected, it is with the voltage regulators. Okay, you can see this kind of the batteries into your school laboratories. Okay, you might have seen. Okay, you can change up the voltages. Suppose at t is equal to 3 seconds, 3 volt is supplied to the battery, and immediately on the 5th second I am going to apply, right, change it to the regulator value to the 8 ampere, sorry, 8 voltages, then the value of the current may change. So in both of the cases, right, okay, if the value of the current is also changing, it doesn't mean that it is an alternating current. No, the value of the supply voltages are getting changed. As of that reason, the value of the current is getting changed, right? So this is having the formula, instantaneous value of current is dq by dt, right, dq by dt, right. Now let's have a very simple example to understand the instantaneous and the average value of the current. Okay, suppose in a specific circuit, charges flowing with time is represented by this equation, right? In a circuit, flow of charges is represented by this equation. Okay, what will be the average value of the current in between t is equal to 0 to t is equal to 3 seconds, while what will be the instantaneous value of the current at t is equal to 4th second? Average value of the current and the instantaneous value of the current, right? Average value of the current and the instantaneous value of the current. So first of all, if I am moving forward to the solution part, right, the flow of the charges, that is equal to 5t square minus 2t plus 4, right, 5t square minus 2t plus 4. So in this case, what happens? 5t square minus 2t plus 4. If I'm talking about the average value, right, then the formula is delta q by delta t in between 0 to 3 seconds. At t is equal to 0 second, right, the number of the charges, see, q at 0, that is equal to plus 4, q at 3 second, that is equal to 9 into 5 minus 6 plus 4, right, 9 into 5, 45, 45 minus 6 plus 4, so this is 45, right, minus 2, so it is 43 coulomb, right. Okay, so it's 43 minus 4 per unit time is equal to 3 seconds. So that is equivalent to 39 by 3. So the average value of the is 13 ampere. The average value of the current, that would be 13 ampere. I heartily apologize if some mistake I have done. Okay, we can just check it out. 5t square minus 2t plus 4 at t is equal to 0 seconds. Charge flowing is 4 coulomb. At t is equal to 3 seconds. 9 5s are 45. Right, minus 6 plus 4 minus 2, 43. 43 minus 4. Right, and that is equal to 39 by 3 ampere. So it's 13 ampere. Now, what will be the instantaneous value of the current at this moment? Okay, this is the first part. The instantaneous value of the current says that differentiating the equation of charge with respect to time, right? So that gives us the instantaneous value of the current, dq by dt. That shows us the instantaneous value of the current, right? So this is dq by dt. Now what happens here? Let's differentiate this. Dq by dt, that is equal to 5t square minus 2t plus 4. So that is equal to 10t minus 2. Right? Okay. We are having time also. It's 10t by 2. Right? By time. Sorry. 10t by 2. Okay. At what second? At 4th second, 38 ampere. At 4th second, okay, the 38 ampere of the current that is flowing through the circuit. So this shows the exact difference between the average value of the current and the instantaneous value. Average value of the current and the instantaneous value. Yes or no? Okay. Now, one question I'm going to give you all into the homework. Right, suppose the flow of the charge, 2 questions, is defined as 3t square plus 4, right? Okay, from a specific point A onto the conductor, calculate the average value of the current and calculate the instantaneous value of the current. The average value of the current in between t is equal to 0 to t is equal to 2 seconds, right? And instantaneous value of the current is 5th second. Right, instantaneous value of the current on 5th second. Yes or no? Okay, instantaneous value of the current on the 5th second. Is it cool? Is it cool? Yes or no? Right. So now, this is the first homework from my side. The next, if instantaneous value of the current, right, or you can say if current flowing into the circuit is represented as, if current flowing in circuit is represented it as 2t plus 4, right? Current into the circuit is represented as, right? Okay, is this possible? The second question is quite important. Is this possible, right, equation for a specific circuit to be true? Any circuit with this value of this expression of the current is possible. How you are going to rectify? This is also the homework based question, but how you are going to rectify it, I'm going to give you all a hint of it, right? Simply just check it out. The charge flowing through the circuit through this formula, I is dq by dt. The reverse process of the differentiation is integration. If we can move up to the current from the value of the expressions of the charges, then reverse phenomena is also possible. We can move on to the number of the charges flowing to the right, integrate by integrating the expression of the current. Just compare it to the value of the NE. If we are having N as the whole number that we have seen into the electrostatics part, if we are having the N as the whole number as we have seen into the electrostatics part, we can say yes, the value of the current is possible. If you are not having the value of the current, right, Okay, if we are not having the value of the n as the whole number, and how value of the n can be into the fractional values? Now, n can't be the fractional value, it should be the some specific whole number, na? Right? So through this current, just integrate it. Okay, integrate it. Or you can just integrate in between t is equal to 0 to t is equal to 1 second. Limits will be needed for the definite integration. Limits will be needed. Okay, t is equal to 0 to t is equal to 1 second. Just integrate it. Okay, replace in this and just evaluate it with the comparing it to the NE. Okay, just find out the value of n. Just note it down whether you are getting the whole number or the fraction value. Immediately just block it up. Right. Okay, so these two are the questions from my side as a homework. Okay, you have to answer all of these homework questions beneath the video. I will be waiting for all of your comments. And guys, you all are commenting less. Though the number of the students, those who are watching our lectures, please comment right beneath the video so we can improvise ourselves. Improvisation is what we can say, the part of our life. It's a part of our teacher. We always used to improvise depending on students, right? If something that is really hampering you all, we are ready to improvise. Okay, it doesn't matter. So please just share with us beneath the video, whatever it is. Okay, it doesn't matter. Okay, now current density. We have seen what actual the electric current is all about, what kind of the supply we are going to deal with in this chapter. Right, after that we have seen what we can say, the average value of the current, the instantaneous value of the current. Now step forward, current density and the relation of the current density with others. Okay, again we are taking one conductor, right? Okay, that is connected to the supply. This is a positive terminal of the battery, right? And this is the negative terminal of the battery. We have taken one conductor connected to the DC supply. Now I'm talking about area 1 of the conductor. I'm talking about area 2 of the conductor. I'm talking about area 3 of the conductor. 3 cross-sectional areas I have taken. Right? 3 cross-sectional areas I have taken to define the value of the current density. Simply, current density is defined as flow of charges per unit cross-sectional area per unit time. Flow of charges per unit cross-sectional area per unit time. Flow of unit per, right, flow of the charges per unit cross-sectional area per unit time. Right. In the previous part we said how many number of the charges are crossing through specific point. But here I want to tell about the entire cross-sectional area of the conductor. Right. Entire cross-sectional area, into this specific cross-sectional area, how many number of the charges are crossing per unit time? Right. Okay. How many number of the charges are crossing through that specific area? Again, I am saying we are taking the example of the PW Vidyapeeth. The gate is there. Through that specific gate, through that gate area, previously I told you all it was a point through which the number of the students are crossing in per unit time. That was current. But here I'm talking about the gate area. That is a difference. Gate point, gate area, gate point, gate area, gate point, gate area, gate point, gate area. Through that gate area, The number of the students that are crossing, sir, emotion, PW, through that specific area, right? How many number of the students are crossing per unit time? So here area is involved, per unit area. So that gives us the definition of the current density. Okay, that gives us the definition of the current density. Flow of charges per unit area per unit time. Right? Flow of charges per unit area per unit time. So mathematically I want to represent it as current per unit area or flow of charges per unit area. Now students might be having a thought, sir, we are broken. Why? You told us that we might be having the two values of the current, the average value of the current and the instantaneous value of the current, right? So is it what really, right, it is included into the formula of current density? Current is included into the formula of current density. It means that somewhere there is a possibility that current density might be having an instantaneous or the average value? Question mark. Question mark. Current density. Okay, I'm going to explain it later. At this moment, I want to explain you all this. This is the value of the current density, right? And this is its mathematical expression. Now we are going to deal with that part. The detailed analysis of it. Okay. For the detailed analysis of how the value of the current density is getting changed, we have to take the shapes of the conductor, right? It depends on the cross-sectional area. How the shape of the conductor is all about will define the value of the current density and will tell you all whether the current density is going to be constant or not. First example, suppose this is the shape of the conductor. The length of the conductor is L. If I'm talking about the all n number of the cross-sectional areas, this is the first cross-sectional area, this is the second cross-sectional area, this is a all cross-sectional areas are same. Now it depends on the supply whether the current density is going to be constant or not. But in this case, if supply is constant, J value is constant. If supply is constant, suppose through the voltage regulator we have selected a value of 9 volt. Until infinite number of the time, infinite time, okay, we have kept as the same. Okay, then being the conductor as a constant, having a constant cross-sectional areas and the specific length is defined, the current density is going to be constant, because in this supply is also constant and all of those cross-sectional areas are also same. So in that case, right, the number of the charges that are flowing per unit time from that specific cross-sectional area is not going to change. From that specific area is not going to change. Right? Second case, right? This is an awesome value. From one side of the conductor to the another side of the conductor, from one side of the conductor to the another side of the conductor, the shape of the conductor is getting changed. So it means that here the value of the cross-sectional areas are getting changed. See, the values of the the cross-sectional areas are getting changed. So in this case, current density is not going to be constant at each and every point. Here constant means that each and every point is the value of this is going to be constant. Same. Constant, it means at each and every point the value of the current density is going to be same. The value of the current density is going to be same. Right? Okay. In the second case, it completely depends on dimensions. Value of J, right, at each point depends on dimensions. It actually depends on the value of the radius that varies in between R1 to R2. The value of the radius that varies in between the R1 and R2. Right? So here J is not constant at each point. We are having the different values of, right, J2, J3, J5, something like that. Third, right, third point. Okay. The third point states that now suppose the shape of the conductor, right? See, basically, right, we are having only 2 points. If the shape of the conductor is getting changed, the value of the current density at each point will differ. If the shape of the conductor is constant and the same, right, throughout, and the supply is kept constant, the value of the G is going to be same at each and every point of the conductor. The second application, the second point that I conveyed, it is having a lots of things. There is a possibility how J depends on area. There is the possibility, right? Here, if I'm talking about the value of the J, how it depends on the area, right? This will define the flow of charges. First, if I'm talking about the dimensions, there is a possibility that J may directly depend on R. With the expression J is equal to constant K as R as the radius. There is a possibility J can be equivalent to what? K R square. There is a possibility that J that be equivalent to K, right, R cube. There is a possibility that J is equivalent to K R square plus K dash R plus 1. There is a possibility that J is equal to J0, 1 minus R by R. For a right current density to be constant, we can easily calculate it is just I by A. The entire mains and advance is all about this second point. Entire mains and advance is all about the second point. How the value of the J depends on the area or a specific radius that will define the value of the current. We are going to see one example based on this. If the length and the shape of the conductor is constant throughout, but if somewhere this is changing, somewhere the current density depends on dimensions and we have to find the value of the current, right, then it would be difficult for us also, because we have to approach to integration and differentiation processes. Things are getting changed, physical quantities are getting changed. It means somewhere the differentiation or integration is involved. Okay, if whenever we are teaching with the basic mathematics lecture, we always used to convey a single thing. What? Somewhere if physical quantity is changing with respect to anything, it means, right, differentiation and integration is going to come. Differentiation and integration is going to come. So let's have the detailed analysis of it. Right, a simple example if I want to take, J is equivalent to J naught R square, right? J, current density depends on J naught R square. J naught is the constant value, right? Okay, J naught is the constant value. Then how you are going to find out the value of the current? Okay, so let's take a very simple explanation of it. Suppose if you want to find out the C, J is equal to DI whole divided by DA. Okay, for the change, if it is a constant, we can simply define it as I by A. But for a very small element, right, I can simply define as DI, that is equal to J of DA, and I is equal to integration of J dot DA. Right? Suppose in this radius is changing to the square value. Radius is changing to the square value. Suppose this is a conductor, right? Suppose here the radius is 1 meter, right? It is changing to the square value. Suppose at 1 it is 1. Suppose at 2 it is 4 meter. Suppose at 3 it is 9 meter. Suppose at 4 it is 16 meter. Like it is where it is changing depending on this equation. Sorry, the value of the current densities. I'm sorry. Not the value of the radius. The value of the current densities are changing like this way. At this, the current density is J naught. Then it is J naught, 4 J naught. And the distances, right, when the radius changes, right, see, when the radius changes, okay, the value of the current density is getting changed. Okay, so in this case, what we have to do, we have to replace this value in the equation to get up to the answers, that I is equal to integration of J naught R square dot dA. How we are going to correlate to dA and R square? For that, we have to take one specific element, the area element. The small area element we selected having circumference 2 pi r with, right? So this will be the value of dA. So it is integration of J naught dot R square 2 pi r dr. So it is 2 pi J naught, right, integration of R cube of dr. So I, it is going to be 2 pi J naught, right, R is to 4 by 4, right, plus C. Okay, this is how the value of the current is defined. A very simple example I have taken, please don't mind. Okay, very simple example I have taken. Suppose if I want to give you all a homework, right? Suppose if I want to give you all a homework, if the value of the current density changes by J is equal to J naught 1 minus R by R for the conductor, how you are going to, okay, right now we are not moving on to the value of the current, just obtain the expression of current. Right, so this is the homework from my side. Right, this is the homework from my side. Okay, so guys, I think please answer beneath the video. We started with the value of the current, average value, instantaneous value, right, current density, detail analysis, current, right, and drift velocity. Okay, I think this much things we are going to see afterwards, right, because to understand the concept of the drift velocity is important to understand the resistances and Ohm's law, right, and it would be quite, see, 1 hour, approximately 1 hour of this lecture is about to pass, right, it would be quite injustice to explain the Ohm's law at the very one moment. Generally, whenever this is the one who starts with the current electricity, they explains the Ohm's law and everything at the right beginning only. But I used to start with the average and instantaneous value of the current. Yes, it happens, right, it went on that, okay, the one lecture has been crossed and still, but it's okay, it happens, it's not a big deal, right. So in the next lecture we are going to move forward to the Ohm's law, the limitations of the Ohm's law, the drift velocity, how current density depends, right, of the drift velocity, and everything we are going to see. I think that much is enough for today, right, as the first part of the lecture, right, as the first lecture it is enough, right. Okay, just be with the flow, right? Again, we are going to come back tomorrow, right? So guys, today it's time to go. This is Indrajit Singh signing off from the desk, and I heartily again apologize for my previous day. Okay, so this is Indrajit Singh signing off from the desk. Bye bye, Sat Sri Akal and Namaste from my side, bacha ji. Bye everyone. Stay at home, stay safe, stay healthy amidst this pandemic. Bye bacha ji.